When we talk about the Space Shuttle, we're not just talking about a machine. We're telling the story of a tragic hero. We're performing an autopsy on a dream. It's a story of incredible ambition, of breathtaking engineering, but it's also a story of compromise, politics, and ultimately, of failure. This isn't just about a vehicle. It's about the very human decisions that created a national icon and sowed the seeds of its own destruction. So, let's get into it. You really have to appreciate what Arthur C. Clarke captured with these words. He was tapping right into the soul of the post-Apollo moment. Think about it. We'd just done the impossible. We'd walked on the moon. So the question burning in everyone's mind wasn't, can we go to space? It was, okay, now what do we do there? The dream shifted from just visiting to staying, from exploration to, well, to occupation. And the shuttle? It was supposed to be the key to that future, the workhorse that would make space feel less like an expedition and more like a commute. And that's the core of it, right there. From the moon to the mundane. The entire goal changed. We weren't just planting flags anymore. The vision was to build things in orbit, factories, labs, maybe even homes one day. The whole point was to make low Earth orbit, well, boring, as routine and accessible as catching a flight from New York to LA. And the Space Shuttle was the tool that was supposed to make all that science fiction into cold, hard economic fact. Now, the original idea, what the engineers first put on paper, it was beautiful. Pure poetry in motion. It was a concept called the DC-3, a fully reusable two-stage-to-orbit system. Picture this, a massive manned booster, basically a rocket-powered mothership, with the smaller orbiter riding piggyback. They'd launch together, the mothership would detach, and then both vehicles would fly back and land on a runway like airplanes. The turnaround was supposed to take just a few weeks. This wasn't a space truck. No, this was the beginning of an interstellar shipping network, the very foundation for an economy in orbit. It was a beautiful dream. But you know what they say about dreams? They have a nasty habit of running headfirst into reality. And the reality of the 1970s was brutal. The Vietnam War was winding down, the economy was tight, and the blank check that NASA had enjoyed during the Apollo years, that was gone. Suddenly, it wasn't engineers calling the shots, it was the Office of Management and Budget. And they looked at this beautiful, fully reusable dream and said, no way, too expensive. So to get anything built at all, NASA had to start making deals. They had to start compromising. And every single compromise was a crack in the foundation. And this right here, this is the whole story in one slide. It's the promise versus the reality. On the left, you have the sales pitch, what NASA promised Congress and the American people. A spaceplane that would fly 50, 60 times a year. A vehicle that would make putting a satellite in orbit cheap and easy. But then, look at the right. That's what we got. A partially reusable hybrid that flew maybe 4 or 5 times a year at its peak. And the cost? It became the most expensive vehicle ever built, with some flights costing over $1 billion. So the real question isn't just what went wrong. It's, was this thing doomed from the start? Was it a flawed concept the second that first compromise was made? Let's dig into what I like to call the 3 original sins of the shuttle's design. First, dropping the fully reusable dream. Instead, we got this giant orange external tank that was just thrown away on every single flight. A massive, expensive piece of hardware just dumped in the ocean. Second, and this is a huge one, the solid rocket boosters. This was a political move to give contracts to companies that specialized in solid rockets. But from an engineering standpoint, it was a deal with the devil. You see, an SRB is basically a controlled bomb. Once you light the fuse, you cannot throttle it, you cannot steer it, and you absolutely cannot turn it off. It burns until it's done. And finally, the Air Force. To get them on board, NASA had to meet their demands. They wanted a huge payload bay to carry spy satellites, and they wanted this incredible cross-range ability to land back at the launch site after just one orbit. That requirement is why the shuttle has those massive delta wings. It's what turned it from a sleek spaceplane into what the pilots themselves called a flying brick. Every one of these deals added another layer of complexity, another layer of risk. Okay, so you've been handed this camel, this horse designed by committee. It's a collection of compromises. And now you're the engineer, and your job is to make it fly. To do that, you have to operate on the absolute bleeding edge of what is physically possible. You have to solve problems that humanity has never even faced before. Let's start with the heart of this beast, the 3 Space Shuttle main engines. To this day, they are arguably the most sophisticated rocket engines ever built. And the challenge starts with the fuel they burn. It's liquid hydrogen. And to keep it liquid, you have to chill it to an unbelievable negative 423 degrees Fahrenheit. That is just a few degrees above absolute zero, the coldest anything can possibly be. Now, literally inches away from that absolute zero cold,
Inside the engine's combustion chamber, the temperature is 6,000 degrees Fahrenheit. That's hotter than the surface of the sun. It's hot enough to vaporize steel.
So just stop and think about that for a second. How do you possibly build a machine that can contain both of those extremes at the same time? A temperature difference of over 6,000 degrees inside one single engine. How do you keep it from either freezing solid or melting into slag? That's the puzzle. The answer is one of the most elegant and terrifying engineering solutions I've ever seen. It's called regenerative cooling, and it's pure genius. Before that super cold liquid hydrogen is burned, they route it through hundreds of tiny little tubes that make up the walls of the engine nozzle itself. The fuel becomes the coolant. It sucks up all that intense heat, preventing the engine from destroying itself. But here's the terrifying part. The turbo pumps pushing that fuel spun at 35,000 RPM, operating under such insane stress that they were always on the razor's edge of exploding. It was an engine of staggering power, but it lived its entire 8-minute life on the verge of total catastrophic failure. And the engineering nightmare didn't stop there. What about coming home? When the orbiter hit the atmosphere, it was basically a flying meteor, with temperatures that would instantly melt any normal aircraft. The solution was the thermal protection system, a skin made of over 27,000 individual ceramic tiles. Each tile was basically a solid block of air, 90% air, 10% silica, making them incredible insulators. But they were also as fragile as a teacup. You could literally crush one in your bare hand. After every single flight, an army of technicians had to inspect thousands of these tiles and hand replace hundreds of them. This process, this logistical nightmare, is one of the biggest reasons the shuttle could never fly more than a few times a year. The dream of a cheap, reusable space plane died right there, in the hands of a technician carefully gluing a fragile tile back onto the orbiter's belly.
But it's easy to get lost in the hardware, the numbers, the engineering. We have to remember people strap themselves into this thing. We have to talk about what it was like to ride this beast. For the astronauts, this wasn't just a machine. It was a living, breathing creature.
Try to imagine it. For the first 2 minutes, it's pure violence. You're being shaken so hard by the solid rocket boosters you can't even read your instruments. It's just a rough, brutal, primal force pushing you into the sky. And then, cut off. The SRBs fall away and suddenly everything is smooth. For the next 6.5 minutes, the main engines are pushing you, gently but relentlessly. Then, main engine cut off. And in a blank, you go from being crushed by 3 times the force of gravity to nothing. Absolute weightlessness. The violent roar is gone, replaced by the quiet hum of fans and computers, and you look out the window. And everything you've ever known, everyone you've ever loved, is on that blue marble hanging in the blackness. It changes you forever.
And the whole point of the program, at least publicly, was to share that experience with everyone. Krista McAuliffe and the Teacher in Space program was the embodiment of that idea. It was a brilliant move, really. It was a way of saying, see, this isn't just for fighter jocks with the right stuff anymore. Space belongs to everyone. It belongs to your teacher. It belongs to you. It was essential for keeping the public invested in this incredibly expensive and dangerous program. And the social impact was just massive. When Sally Ride flew, it wasn't just another mission. It was a cultural earthquake. For millions of young girls watching on TV, it completely redrew the map of what was possible. It was this visible, undeniable proof that the sky was no longer the limit. And you saw the astronaut corps itself begin to change, to look a little more like the country it came from. The shuttle was the vehicle that made that happen. But there was a dark side to all this success. A dangerous mindset was taking root inside NASA. The constant pressure to meet launch schedules, to prove the shuttle was operational and worth the money, created what investigators would later call a success-oriented organization. What that really means is that they started explaining away problems. Things that should have grounded the fleet, anomalies that engineers were screaming about, were slowly reclassified as known acceptable risks. They started believing their own PR, and that institutional blindness would have devastating consequences. On January 28, 1986, all those compromises, all those accepted risks came home to roost. The launch of Challenger was a national event, watched live in schools all over America. And if you listen to the cockpit audio, it's just chillingly normal. They're just calling out altitudes and speeds,
Everything is going perfectly. Until, at 73 seconds, the pilot, Dick Scobie, says, "Uh-oh." That was the last thing anyone ever heard from the crew. The investigation quickly zeroed in on one of those original sins, the solid rocket boosters. Specifically, the rubber O-rings that were supposed to seal the joints between the massive segments of the booster. But here is the most damning part of the whole tragedy. This wasn't a surprise. This wasn't some unforeseen accident. Engineers at the company that built the boosters, Morton Thiokol, had been waving red flags for years about how these O-rings could fail, especially in cold weather. Their warnings were ignored. Management overruled them. The flaw was known. The risk was normalized. The disaster wasn't an accident. It was an inevitability. And the moment that drove this truth home to the entire world came from the physicist Richard Feynman during the public hearings. It was pure genius. While NASA managers were showing complex charts and using bureaucratic language, Feynman asked for a C-clamp and a glass of ice water. He squeezed a piece of the O-ring material in the clamp, dipped it in the ice water, and showed everyone watching on TV how it lost its resiliency, how it failed to spring back. In one simple, elegant demonstration, he proved to the world what the engineers had been saying all along. He cut right through all the layers of management and exposed the truth. There was a fatal disconnect between the people who knew how the machine worked and the people making the decisions. The shuttle did fly again. It flew for another 2 decades. But the story doesn't have a happy ending, because in 2003, we lost another orbiter, Columbia. And while the physical cause was different, a piece of foam insulation, not an O-ring, the root cause was exactly the same. An organization that had, once again, learned to accept known risks. A culture that normalized deviance. It forces us to look at the shuttle's legacy, not just as a triumph, but as a tragedy in 2 acts. Because here's the thing. For all of its fatal flaws, the shuttle was an absolutely incredible machine. There are things it did that no other vehicle in human history could have done. It gave us the Hubble Space Telescope. Its giant payload bay was the only way to get it into orbit, and its robotic arm was the only way to fix it when we discovered the mirror was flawed. Without the shuttle, our entire understanding of the cosmos would be different. It built the International Space Station piece by massive piece. It was a deeply, deeply flawed vehicle, but my God, it was also magnificent. So why do it? Why take these incredible risks? I think Stephen Hawking put it best. This isn't just about adventure or national pride. Ultimately, it's about survival. The long-term survival of our species depends on not keeping all our eggs in this one planetary basket. So when you look at it through that lens, was the shuttle a necessary evil? Was it a brutal, painful, but essential lesson in just how hard it is to actually live and work in space? And that's the question we're left with. It's the core of the shuttle's legacy. Was it a magnificent failure? A 30-year cautionary tale about how politics and budget cuts can poison an engineering marvel? Or was it a flawed pioneer, a trailblazer that, through its own tragic failures, taught us the hard-won lessons we needed to learn to build the safer, more reliable spacecraft we have today? There's no easy answer. The only thing that's certain is that the Space Shuttle holds its place in history as a true tragic hero in our long journey to